So magnets have a field around them just like charged objects and just like gravitational objects. And there is a direction that's assigned to that magnetic field. So we're going to start with something simple. We're going to start with a bar magnet, okay? Starting with a bar magnet. Similar to electricity, magnets have like and unlike properties. Instead of charges, what do we call those like and unlike properties? Poles, that's right. So there's always a north and a south pole to a magnet. The magnetic field that surrounds the magnet is always strongest at the poles. And just like gravity and electricity, when we draw field lines, the density of those field lines is proportional to the strength of the magnetic field. So if you've ever played with a bar magnet or even magnets on your fridge, or there's little like spheres that are magnetized that you can make cool stuff with, even spheres have poles. And those little spheres will rotate in such a way that the poles interact, because that's the strongest point on a magnet. So these lines represent the magnetic field, okay? And like conventional current, we have to decide direction for magnetic field lines. So, you know, they decided backwards for current, right? Conventional current was out of the cathode into the anode. We know that that's not really how it works. Magnetism, you don't really have to worry about that. There's really, truly no right or wrong direction for magnetic fields. Magnetic fields either attract or repel, and that depends on the nature of the poles, right? So the standard is out of the north into the south. So that's the direction, out of the north into the south. And the field density will always be greatest at or near the poles. Now, there's more than just these field lines, though. There are other field lines that like curve around and do that, curve around and do that. So similar to, remember we had electric fields and I had two like charges versus opposite charges. You're going to get those kind of patterns. Okay? But out of the north into the south, out of the north into the south is always how those field lines will point. Okay? Instead of using like a point charge or a little test charge to test magnetic fields, what we do is we use a small magnet, sometimes referred to as a compass. And a compass is just a magnet that's it's basically like a little teeny teeter-totter sitting on a pivot point, and it's allowed to freely rotate. So if I were to put a compass in this magnetic field, it would align itself tangentially with the field lines. So that's like a little compass. There's a pivot point, and it'll look like this. Okay? So it will align itself with the field lines. If I put another one here, it'll do the same thing. It'll align itself. I'm just drawing it a little bit bigger outside the compass like that. Now, why am I using a small compass? Why not a nice big old compass? There's a reason. Perry?
Because the compasses themselves can't act as magnets.
Right. It's like the test charge. You don't want the compass itself to have such a strong magnetic field that it deflects those field lines, right? So that's what we're going to use, these little teeny tiny baby compasses when we demonstrate magnetic fields, okay? The field lines will follow the arrows. So they point, let's put a compass close to this North Pole, right? So they will point out of the north, see? And then into the south. Now, these little sort of test compasses, what the arrowhead is what pole on the compass? So this, what is this the north or the south end of the compass? Yeah, it's north because opposites attract. Does that make sense? So if it's pointing toward the south end of a compass, that means it's the north pole on the compass itself. This gets a little bit confusing. I think you can understand it, it's just the wording gets a little bit cumbersome. Okay?
North pole's pointing to the south pole on the compass, on the opposite side of the north pole.
Yes, that's correct. Okay? So the compass follows the magnetic field lines.
So then why do our compasses always?
This is an excellent question.
Is it the south pole that has the arrow on it?
Yeah, that's a good question. So our compasses are aligning themselves with the Earth's magnetic field. All right. So I want you to imagine that there's a big bar magnet buried in the Earth.
Wait, is there? Yeah. Big bar magnet.
There is not. I want you to imagine there. So we're standing here in Michigan, and we're holding a compass, and it's pointing to the north, right? Now, using this rule, the north end of the compass is pointing up toward Canada, right? So if that's a north pole, then which end of the bar magnet is buried in northern Canada? Right. So it's backwards logic. We're in backwards land. The north magnetic pole on the Earth is the south pole.
No.
Now, I hope you all realize that this is totally arbitrary. There's really, what's the difference between north and south? Exactly. You can call it whatever you want. We just have.
Wait a second. The north pole is the south pole?
Yep.
What's that?
Where's the same pole?
This is not real, Matt.
What?
Isabel!
What?
Were you that kid in kindergarten?
No, I was never.
I can see it.
All right.
No, I was like, that's creepy.
Oh, were you?
Creepy.
It is a little weird. Like
It comes and takes your teeth, like, they're
sneaking into your room at night. I know.
Yeah, I just thought.
Out of
it
your
was
mouth.
That would be also scary because that kind of.
Okay. So, listen guys, since there isn't really a bar magnet buried in the Earth, what causes the Earth to have a magnetic field, and by the way, it's a dang good thing that the Earth has a magnetic field.
Yeah.
And it's not just about being able to find your way in the woods.
Polar radiation. Out the water, too.
The drinking gore, oh yeah. All right. So, there's the Earth. This is the,
North pole, which is the south pole?
no, this is the North Pole. This is the North Geographic Pole.
Ah.
This is where Santa lives. That's the North Pole. You guys know there's not actually a pole there, right?
Yeah.
Okay.
They really don't have.
It's a little chilly and the ground's very hard, so.
They're trying to find a pole buried in the ground.
Gotcha. So the North Geographic Pole is not the North Magnetic Pole. The North Magnetic Pole is somewhere in northern Canada. And that's actually the south pole of a magnet. So it's called magnetic north.
All right, so if we go to the exact north geographic pole, our compasses will point south.
That is correct.
But it's going to say north. Oh, okay.
No, it'll say south.
No,
Because the compass is going to behave like it normally does.
we're going to be north of the
Yeah.
actual north pole, even though
Yeah.
we're at the north pole.
Yeah, your compass will point, if you stand on the North Geographic Pole, your compass will point south-ish, depending on where, So, this is magnetic north. Magnetic south is, again, not quite at the south pole, but magnetic south is down here.
But it's covered in ice.
Magnetic north is
Yes. So this is, let's draw our pretend magnet, okay?
Is that actually pretend? I still don't know if
It's pretend. Okay? So do you see what's going on here? The way we identify magnets, which is completely and totally arbitrary, it's just a way for us to agree, just like conventional current, just like, hey, electrons are negatively charged. You're just believing, Mr. Luckreth, that they're negatively charged. It's just an agreement within the scientific community. They're not necessarily negatively charged.
Protons could be negative.
Absolutely they could.
And then we bring up, hello, sir.
Is anything real?
no.
All right. So what do the magnetic field lines around the Earth look like? Out of the north, into the south. Out of the north, into the south. Out of the north, into the south. Let's see. Into the south. It is beautiful, isn't it?
So does it feel different when you're in magnetic north?
This is an excellent question. So this is the way the field lines point. You got it? Out of the north into the south. So the reason for this is that we identify, traditionally identify the north pole of a magnet, and it points north. Does that make sense? So remember, from this, when we put our little compasses, which are kind of like the test charge, these little magnetic free-moving compasses will actually point toward magnetic south. Does that make sense? So when they do that, when you put a little compass, if I stand here on the equator, let's say, and I look at my little compass, it will point parallel to the field lines, and that'll be due north, right? So that's why it's done that way, or that's why we agree. Now, this has a huge impact on our ability to survive on this planet based on the biological beings that we have evolved to be, okay? There is tons of radiation out in space. And there are limits to, like, how many hours per week flight attendants and pilots can fly, especially when they are flying in, like, commercial jets high in the atmosphere, because that radiation, you get more radiation when you're closer to the sun, closer to space. We have two things that shield us from that cosmic radiation. One is the atmosphere, okay? The other is the magnetic field of the Earth. So, when cosmic radiation, so that's all those electromagnetic waves that we talked about given off by not just our sun, but by every star that was ever created in the universe, starting with the Big Bang. So all of that radiation is traveling through space. It can travel through a vacuum. And so let's imagine, ooh, there's some electromagnetic radiation, right? Oh, electromagnetic radiation. Oh, no, dangerous like gamma radiation, right? And when it hits both the atmosphere, some of it will be absorbed, but when it hits that magnetic field, this is what radiation? Magnetic, electromagnetic radiation. So when you put two magnets together, what happens? They can repel or they can attract, but really what happens to a vast majority of this is it gets sort of skipped off back into space, okay? So it's like, and it depends on the angle, okay? So the Earth's magnetic field has a shielding effect. If this was gone, what would happen to us? We might turn into the Hulk.
We saw that triangle there.
Are we going